Welcome back to Software Requirement Engineering. Now in this lecture we're going to look at the behavioral perspective of software system. In behavior modeling, we want to show the different states that a software system can be triggered by an event or an activity. The state of the system can be of any levels. It can be from the level of an object, level of components, to the level of the whole system. Behavioral modeling emphasizes the states and transition between states of one single entity, and this is the distinct criterion between behavior modeling and data modeling as well as functional modeling. It is to show the states of one entity. So let's not waste time. Let's begin with the first behavior modeling language, finite state automata, briefly, followed by FST briefly. We'll be looking at more in more details in state chart, and finally some examples in UML State Diagram. Finite state automata has two variations: deterministic finite state automata and non-deterministic finite state automata. Look at the notation. The start of the state is indicated by the start arrow, and then the end state, the final state, is indicated by arrow with double boundaries. And to move from one state to another state, we need a transition, whereby the transition is labeled by an activity or an event. In this case, the event or the activity will be represented by transition functions, which takes an input that will trigger the transition from one state to another state. Now, as mentioned earlier, there are DFA and NFA. DFA is deterministic and NFA is non-deterministic. Now, DFA, deterministic, is more straightforward. The entity can only have one state at one time, only one state. Now, if you look at the traffic lights, is it possible for the traffic light to be in any two states? For example, like we can have red and green together, or red and yellow together, or yellow and red together. Is it ever possible? No, right? It has to be in only one state at a time. This is what we mean by deterministic finite automata. It has very unique event state, and then the event, the trigger that makes the traffic light changes the color will be timer, or maybe events like when there's no power, then it goes to off state. That will be the trigger. Now, how about non-deterministic? Non-deterministic finite automata is a finite automata that allows multiple states. Allow multiple states for a system to be in. Now let's look at the diagrams below, DFA and NFA. Now take note that NFA, for state 0, it can move back to itself, or it can move to state 1. And what will be the trigger? The trigger for state transition will be H. So the input H will trigger the transition function to shift it from S0 to S1. But at the same time, the input H is also available here for this transition function. So when there's a presence of hash, S0 can become itself. It can also change to state 1. So there are two different target states here, S0 and S1. Now for DFA, it is very unlikely, it's not possible for this to happen, because there will be no more than one trigger for different states. So you see, H triggers uniquely for state 1. Hash state is uniquely for S1. Unique event state for deterministic, but not so for non-deterministic, whereby the hash will trigger to S1 or back to itself, S0, through the hash input event. So that's the distinct mark between DFA and NFA. Now let's move on to the other type of behavior modeling. We are moving away from finite automata to finite state transducer. Finite state transducer is similar to finite state automata, except that it also has output function. Now in this case, if you look at the notation, yeah, it takes parameters, and it also generates the output. Now in this example, we generate output X, generate output N, generate output A, generate output S, which is not present in finite state automata, but yes in finite state transducer. And there are two types, merely and more. In more, you only take the previous state as the argument, as the input for the function to trigger this change of state. But in merely, it's taking more than two inputs, the previous state and another external input. That will be the difference between merely and more. Merely takes two input, the current state and another input, whereas for more, it takes only the current state, only one input. Let's move on to state chart. State chart is used because finite state automata, FSA, and finite state transducer, FST, they become very complex when you use them to illustrate a complex system. State chart provides a cleaner diagram. State chart is used to structure the state spaces in hierarchies. You see, these are the strategies to make it cleaner, because you can place the different states inside another super state to simplify it. You can define the condition for transition. You look at this example. From inactive state, it has two possibilities, no GPS signal or GPS signal. If it has no GPS signal, it goes to this state. It has GPS signal, it goes to another state. So we define conditions for the transitions. It defines action for states and transitions. If you look at this example, you see the state is enriched with additional information such as enter and exit. So it defines during the entry of this state, these are the actions to be done. When we're exiting this state, these are the entries to be done. Now, have you look at some programs whereby when the program is when a system is in particular state, it will erase the old file and the previous file, so that when the algorithm is being executed, it's going to write a new file instead of the to overwrite the old one. So the entry of that state will execute the action to delete the previous file, right? So we can have entry, exit, and throughout. Last but not the least, state chart also allows concurrent behavior. So in that one state, you will split it into half. That will allow two different substates. Yeah, we allow two different substates. It's not a choice between left or right, but both are being executed at the same time. So it allows concurrency. State chart allows concurrency. So I've mentioned earlier, state chart allows condition. You see, from this state, we have three possible conditions that will lead from this one state to three possible other states. This is another way to show condition. Okay, when an event trigger, okay, this condition state will determine either P, Q, or R as the eventual target state. Yeah, this is another way to draw condition state. Okay, now let's look at this example of a GPS system. This is a starting state. Input, when the user input of destination, these are the actions. When this state is being entered, the input device will be turned on. When this state is being exited, that means it's moving to another state, then the input device will be turned off. And throughout the whole throughout the whole period of that state being active, it will process the input. Yeah, so this is the properties that enrich the state with some actions. Let's look at one example of a system that scans the barcode, and then it's going to display, it's going to print the receipt. So the system is ready, in the ready state. This is the default state. When we start the scanner, these two actions will be executed concurrently, scanning the barcode and weighing the goods for the weight. And after that, there will be two possible routes, two conditions. If the cashier opens cash tray, then it's going to execute this. If the cashier receives a credit card and the cashier actually swipes the credit card, it will trigger this state. Yeah, either one of these. And finally, it will print the receipt, and the machine will be back to the ready state. Now, some systems will have history, will have memory of the previous state. So in this case, the system won't start with the same starting point every time, because it remembers its past, the last state of the system before it's been turned off. In this example, you see the login screen. During the login, you remember the previous state, whether the password has been entered 1 time, 2 times, or 3 times. So it remembers. If you have entered 3 times, that will lock the user. It shows that the system has memory, and for this to be implemented, the requirement must show that it has history state, history annotation. So far, we have covered a few behavioral modeling languages. They are finite automata, finite state transducer, and state chart. The next notation, perhaps the most important for this lecture, will be UML State Machine Diagram, or sometimes for short we call state diagram. State machine diagram is based on state chart notations. Take a look at the figures in the bottom half of this slide. Note the similarity of the notations used in state chart and notations used in state machine diagram. Within the rectangle is the name of the state. One may also enter the actions in the body of the state. Likewise, the same notation is being used in state machine diagram, with only a little bit of syntactical differences. The transition also shares very similar syntax. In both, there will be a part for the trigger, and there will be a part for the action carried out by the system. If one remembers, this is very similar to finite state transducer merely notation, which contains the output of the transition function. In this case, even though it's not an output, but it is an action. Notice that even though the syntax may be different between transition notation used in state chart and transition notation used in state machine diagram, semantically they are similar. In state chart, an event is a condition. If it's true, then the transition occurs and the action will be executed. In state machine diagram, the trigger is a condition. If the condition is true, the transition will occur and activity will be executed. Let's look at example for both state chart and state machine diagram on the right hand side. This example shows a navigation system for perhaps a car. The system will change state from input of destination to calculating the route. This only happens after the user enters the destination. This will be the trigger if the user enters the destination. The activity that follows that will be the system storing the destination and the change of state from input of destination to calculating route. Now, when the state of calculating route is achieved, at the point of entry, at the point of the state being triggered, the system is going to delete the current route. And during the process, even though it's not notified here, it's going to override with new route calculated. Not during the transition, during the exit. During the transition, it's calculating the route. During the exit, the route will be stored. Likewise, during the input of destination, when this state is triggered, the entry will turn the device on. It will process the input from the user, and upon change of state from input of destination to calculating route, the device will be turned off. The input device will be turned off. More notations for state machine diagram. State machine diagram, as compared to state chart, is focused on reusability. That is the distinctive criterion that will help us set state machine diagram apart from state chart. State machine diagram provides hierarchy of states. In this state are states. Take a look at this example. This is the default state at the starting point, ready state. When the trigger starts navigation is received, the state will transit from ready to navigating. Navigating state is a hierarchy of substates, which are input of destination, calculating route, tracking waypoints. The other difference will be the use of termination symbol. In state machine diagram, the termination symbol is indicated by a darkened circle with an extra boundary, sort of like a halo around the circle. It determines the final state, termination of the process. Last but not the least, this is not a conclusive list, not an exhausting list of differences, is the use of submachine states. In this case, the symbol here that looks like a pair of spectacles indicate that switch state contains submachine states, which, if blown up, will look as follows. To understand submachine state diagram further, let's look at this example. This is the similar example for car navigation system. The starting state of the car navigation system is ready, as indicated by the start notation. From the ready state, you can proceed to navigating state. When the trigger navigation started occurs. Navigation started could be a press of a button on the screen of the car navigation system. From a navigating state, the next state would be ready. If the navigation is cancelled on purpose by the user, or if the car has reached the destination, and we go back to the ready state. So this is a conditional transition, either navigation cancelled or destination reached. Another state shown in this example is a current position. In order for the navigating to occur, it requires two conditions to be fulfilled: having the navigation started and having the position acquired. So these two states are two prerequisite states before navigating state could be triggered. Navigating state contains substates as indicated by this symbol. The blowout of navigating state is as displayed in this huge rectangle. This is the label of the state navigating. The substates are input of destination, calculating route, and tracking waypoints. The first substate in navigating state is input of destination. Upon entering destination, the system will calculate the route. Calculating the route will provide the tracking waypoints. Tracking waypoints will be used by the driver to steer his or her car to destination. And this state will be maintained until the navigation is cancelled or the destination is reached. However, the tracking waypoint state can also be diverted in case of deviation. This happens when the driver does not follow the waypoints and has moved to a new location. This will trigger the system. This deviation will trigger the system to recalculate the route to establish new tracking waypoints. And this will go on and on until the navigation is cancelled on purpose by the user, or if the destination or if the driver has reached the destination. Then it will go back to the ready mode. Even though not shown in this diagram, the ready state could be turned off by having another off state and a trigger, then switch off. So that's all we have for state machine diagram. I hope with this example it will help you to understand the difference of state machine diagram as compared to state chart. You also should realize that state machine diagram is based on state chart. Prior to state chart, we have finite state automata and finite state transducer. Because these two earlier modeling notations are not convenient for complex system, therefore state chart and eventually state machine diagram are introduced. The difference between state machine diagram and state chart is that state machine diagram is more convenient for reusability. So I hope you will revise on this on your own and practice drawing some examples of state machine diagram to familiarize yourself with the notations. The next perspective of solution-oriented requirement will be functional. See you then.